Welcome to the introduction video of SheepMetal. In this video we have a look at all these components and how SheepMetal works in its basic form. So let's have a start with the already set BREP. So this came out of a different CAD program, and at this point it's just a BREP. So with the manifold to sheet component we can simply convert this BREP into a sheet data structure. So to make this work we have to set a root face. So let's do 1, so that will automatically decide the root face. If you want to have more control over the root face, which is sometimes quite important, I would suggest to define a strict root face. So let's quickly see which face we should take. Probably phase 1 will be a good phase to go for. And so now we have the basic data structure. So from here on out we can use, for example, the custom sheet parameters. And from here on we can also start using this data structure. So let's have a look at the different types of flanges and features. So here you see in green, for example, that's the root face that we defined before. Then in blue we have the different bends, and here we can also display the different bend directions or the bend grouping, as you can see here. Like if they get likely same bended, we can do that there. And also we get labels for each of the faces, so that can be used later for fabrication. We can also decide on just displaying one side. So that's the first side. The first side is always the one with the root face. And then we have the second side, which will be the opposite side of it. The output will be different BREPs, and we can also filter through it all. So let's have a look at the unroller. The unroller is basically you plug in a sheet and decide on a compensation strategy. So there are different ones. We have then directive sensitive K-factor and also just angle-based K-factor. So for this you need already quite a bit of data. But for the sake of this video, let's keep it just as a plain number. And so you can see the unroller part. In addition, we can also find some information about unrolled result, as for example the bend angle, bend directions and stuff like this. So to help us further, let's also add some annotations here. So now we can see the labels on each bend, so we can properly assign values to them. So that was already the first part. So let's have a look at how to convert a polyline into a sheet itself. So the base will be just a plain polyline. And now we can define different features of that polyline to sheet. So we define a thickness. We can define a bend radius. And now we can also just define a simple depth of the sheet itself. So from here on we can just use this sheet again for unrolling, for analyzing. So now let's plug this also in on the unroller, and now we can see again the unrolled sheet part. So to also quickly have a look at the K-factor. Let's add a slider here, and so we can see what's actually going on here. So yeah, now we can see how it's compensating for the bend. So in the second part we focus on how to create a sheet from ground up. So for this we have different tools. For creating this non-manifold BREP first. So let's get started with a base rectangle. And now this will be basically the base for our sheet. So now let's turn this into a surface. So from here on we start to use these helper components. So we have like the non-manifold flange and the non-manifold hem. So for the moment we will start with the flange. And so what we will do is basically plug in the surface itself, and then we have to define an edge index. So that will be basically a edge of this surface. So for now, let's use 0. So now we can also define further attributes, for example, the height of the flange itself. So that will be our little flange. And now we can also define the angle. So now it's in radians, but you can also set it to degrees. We can also flip the BREP and also define a setback from start or end. And let's create another one here. So let's use the edge 2 of this space and no setback. And let's flip it as well. So now let's merge everything together. So now we can use the non-manifold to sheet component and plug in the raw non-manifold surface, and we get a sheet. So this component will basically apply bend radii to the sheet or to the non-manifold surfaces, and then also thicken everything up and apply relief cuts, as you can see here. So now we also have some options for the bend reliefs themselves. So we can use the options here. So we have like flat, filleted, so it will be flat, filleted, and also rounded. So now we can also set the setback. So I think by default it's 1, but we can adjust it by setting the number here, so you can see how the setback is changing. The extension property is used for holes inside the sheet, so if you need release cuts there. And here we also can set the circular radius of the relief cut. Let's add as well a hem here. So adding hems is a bit more complicated than the rest of the creation process. So there is a helper for it. It's called non-manifold to hem, and we just plug in a base surface again. Here we use the flange. We decide on the edge index, so let's use 0 for now. We decide the hem height, so that's the basic height of the hem. And then now the more complicated part is the hem gap. So the hem gap is basically the distance between the flange and the hem, basically. And so let's use 0.1 for the beginning and plug that in. So we also have the from start and end as with the flange. And now we can already see I used the wrong edge index since it's now on the side. So let's change that quickly. So now we have a proper hem. So let's add it as well to the non-manifold surface. And here we can already see there is an error, and that's because we haven't told the plugin for what hem gaps that it has to look for. So at the moment it doesn't automatically happen, so we have to tell it explicitly what the hem gap is. So that will be 0.1 here. So let's add this to the hem detection width. And so it's still an error because like at the current state it will intersect with the offset. So depending on the flip offset, it will work or not. So let's flip it and you see it's working again. So that's something to consider. So to make that work on the other side, we have to basically put 2 times the thickness plus the hem gap, so that doesn't collide with itself. So let's also add this. So as you can see now it's working. So that's something to consider while designing the sheet, to be careful that it doesn't self-intersect while offsetting. So sometimes you need just the hem gap, but also sometimes you need 2 times the sheet thickness with the hem gap. So let's do some little calculations to automate this process a bit. So if we change the thickness of the sheet, it will not directly fail again. So from here on, we can just use it as a sheet again and just plug it into the unroller. In addition, we can also explode the sheet. This will just destructure the sheet itself. So here the mistake was to plug it into a BREP component, which converts it in a BREP. But we don't want that at this stage, so we should use the sheet parameter if we use that, or the data parameter, that will also work. But now let's use the sheet parameter here. And now it's working, and so we can like properly destructure the BREP itself. So now you can see the destructuring happening. In addition, we have tolerance attributes, so you can set tolerances here manually. So if you need different tolerances that is not defined by Rhino, for example in Rhino Compute, you can set this here. So in addition, you have a changelog component where you can see the version and the changelog of the last update. And so this is the first overview of SheepMetal. So if you have further questions, I would suggest looking at documentations that is linked below, or add comments on Food for Rhino.